the point of view of, which bulk theories are actually the good bulk theories. And this is related to the sort of the relationship between what we usually use as Euclidean and Lorentzian methods in the context of gravity. Good. Okay. So this is the lecture number 3. So when I say the relation between Euclidean gravity and Lorentzian gravity, what I really mean is the Hilbert space formulation of quantum gravity and the path integral formulation. And usually, of course, there's some direct derivation of the path integral from the Hilbert space formalism of any quantum mechanics. I mean, that's how Feynman derived the path integral. But it's if you focus on the sum over saddles of the path integral, it looks like a non-trivial reorganization of the problem sometimes. But when we discuss Euclidean gravity, the Euclidean gravity path integral, one's really violating the rules of the game of how one would have originally derived path integrals from the Hilbert space. And the point is that when we discuss the Hilbert space, including in quantum gravity, we always have to imagine that there's some spatial slice times time, and we may fix temporal gauge, at least in perturbation theory, in some way, and discuss gravity in a kind of canonical formalism, and then quantize that. And so it's always associated to space-times with some defined foliation. But when we study Euclidean gravity, we discard that, right? We don't demand that, when we discuss the Euclidean black hole, we don't demand that the Euclidean Schwarzschild solution is foliated by the spatial slices that look like the spatial slices of the black hole we were trying to discuss. So somehow the rules of the game get shifted when going between the Hilbert space formulation and the Euclidean formulation.
Yeah, even here, I mean, the Lorentzian is quantum mechanics, right?
Right.
But in gravity, of course, Hamiltonian is could be zero.
Yeah.
And space could be closed.
Yeah, yeah. Mm-hmm.
And then one doesn't really know what to do.
That's true.
Right?
Yeah.
So the starting point is already restricted to some special case.
Right, and so indeed today I'm only going to talk about situations in asymptotically flat or really asymptotically ADS is what I'm going to talk about. Yeah, I think if we have closed universes, the most likely Hilbert space we should associate to the global system is a one-dimensional Hilbert space, because we only really know one state, which is the Hartle-Hawking state. To make any other state, you have to insert something into that path integral, but there isn't anything which is non-perturbatively diffeomorphism invariant, because when you integrate it, will hit the cut boundary where it's supposed to define the state.
You need the observer sometimes.
So you need the observer, and I will talk about that a little bit in 2 days in the last lecture. But I won't have anything deep. I mean, I won't answer anything about the pseudospace, but or closed universes, but yeah. So that's
here's really a question of how do you do with rotation in geometry?
Yeah. Good. So yeah. So that's the hardest problem, but we'll start with something where we have more of a handle, so we can proceed. But even though the rules we use under the label of Euclidean gravity don't seem to follow from just doing the Wick rotation on the foliated Lorentzian Hilbert space formulation, they give us answers that we like. They seem to big, beautiful answers. They agree with, in the context of ADS-CFT, they agree with the quantum computations.
Some understanding of the fact that the integral doesn't exist. I mean,
Oh, yeah, well, yeah, well, what I mean is when we do this, we usually look at saddles.
Yeah.
We don't do the off-saddle integral. So take some sum over saddles, and this seems to give us a very nice answer. And in fact, it's kind of a miraculous. We kind of get much more out of the answers than you might think, because very often the saddles of the Euclidean problem are in a semi-classical regime where it seems that the long-distance effective theory tells you the answer for something that sounds like a microscopic property of the underlying theory. That, why would the long-distance theory even know the answer? So it's kind of, looks beautiful, so I'm not trying to suggest there's something wrong with what we do, but the question is, how do we reconcile these two? How do we reconcile these things? So let's just start with the oldest example, which is the Euclidean black hole. So when we discuss the Euclidean black hole, we might think we're computing the trace over the gravitational Hilbert space, if we know how to define it precisely, of states that look, like an asymptotically ADS black hole configuration. I want to take the trace over them, weighted by the asymptotic Hamiltonian. So an asymptotically ADS. And then the rule of Euclidean gravity says that we find some saddle which has this topology. It looks like a disk in the time direction, which is this way. This is radius beta. This is the radial direction. And then there's some angular sphere that I'm not drawing, if we're at ADS d plus 1. And this sphere just goes along for the ride, and it's like the horizon manifold. Here it has some minimal size. Okay? And it's not contractible at this point. Instead, the Euclidean time circle is contractible. And this saddle, in fact, precisely because the Euclidean time circle is not contractible, it gives an on-shell action which is not just proportional to beta, the way it would if I had a classical solution that was just periodically identified with some radius. And so therefore it gives a non-trivial contribution to the entropy. The entropy is, the beta d beta minus 1 of the partition function. And so if I have terms proportional to beta, they cancel out the expression for the entropy. They just correspond to renormalization. They just correspond to the ground state energy. Right? But because the time circle here shrinks, it has a different kind of dependence in the on-shell action on beta, and gives a non-trivial answer for the entropy.
Sorry, do you mind just saying what the Euclidean prescription is in general?
Oh yeah, by the Euclidean prescription, I mean we fix the boundary data and then we sum over everything. And maybe when we discuss saddles, it means that we just only consider saddles. We do perturbation theory around the saddles and sum them up.
And that should give the partition function.
And that should give the partition function. That's the Euclidean. That's what I mean by the Euclidean prescription of the partition function.
And is the mass, like the ADM mass, is that part of the boundary data or no?
Well, it depends on the problem. Here I'm imagining ensembles where you fix the temperature, because that's the more conventional boundary condition, and then the mass is, the ADM mass is this H. So, but you could do a Laplace transform of this quantity to fix H instead of beta, that's fine too. These are like dual boundary conditions.
I think that
We could say in a different way, in the gravitational language, on the ADS boundary, we usually have in mind some Dirichlet boundary conditions for the metric, and that we fix the time component of the metric, so that fixes the length and that fixes the temperature. But we could also take the dual boundary conditions where we fix the energy and we let the metric fluctuate on the boundary.
okay, but you called this a Euclidean black hole, so it was a black hole before you summed over this saddle, right?
Okay, so maybe I should back up a little bit. So, I mean, if we look at the ADS black hole, this means something. Here's the Penrose diagram. Here's the ADS boundary. There's some horizons, and this is the outside the horizon region of ADS Schwarzschild. And then, well, we could try to continue it. We get the two-sided black hole, or maybe this is the exterior of a black hole that was formed from collapse or some other state with something else behind its horizon. And we want to count the states that look like this. and the the kind of naive Wick rotation of this region outside the horizon, this has a symmetry associated with Schwarzschild time evolution, where if we go up in Schwarzschild time, it's on trajectories like that, right? And if we analytically continue in this time, we get this Euclidean A Schwarzschild. But because there's the dashed line here is the horizon, where this T component becomes null in the metric. It's a line in Lorentz signature, but that turns into this point in Euclidean signature and it caps off the space. So that's the relation of this picture to that picture. Did that answer the question?
My question was actually, so you said the example we're going to take is the Euclidean black hole. So
Right, this is supposed to be this picture.
okay, but that's already a saddle in this partition function that you're calculating.
Yes.
So this is an example of a saddle. Is that what you mean, or
maybe to clarify, I mean, whenever we're talking about an entropy, we want to compute a thermal partition function and extract from it the entropy, for example. In Lorentz signature, there are many states, right? When we're discussing entropy, many kinds of states, and they're not time independent. It's like there are many time dependent states. So there are many. This is a time independent picture. That's extremely special in Lorentz signature. That's not the only state we want to count in Lorentz signature when we say we want to count the partition function. Just like if we want to count the partition function of the gas in the room, we do not only count static configurations. Most of them are not static. Most of the states we want to count are not this, but they're black holes formed from collapse. That defines the ensemble. But then when we do the Euclidean path integral, and we evaluate the path integral by saddle points, it's typical that the saddle is time independent. And then, let's say we're trying to compute the entropy of a harmonic oscillator, then the Euclidean saddle, so in a harmonic oscillator there are many states, right, where the thing goes back and forth. But if we could try to count those states by doing the Euclidean path integral, then we try to find the Euclidean saddle, and it will be the trivial saddle, that x equals 0 always. That's the saddle. And the whole, it has oscillation of 0, and the whole answer comes from the fluctuation determinant around the saddle. And from the harmonic oscillator, it's quadratic theory, that's exact. It's one loop exact. In the gravity case, we found this. If you try to find the saddle, you find this interesting geometry, which looks like the Wick rotation of this particular time-independent outside the horizon region, but it's supposed to, by the general logic of path integrals, capture the whole answer if we include this and the perturbative corrections around it. Plus, if there are other saddles, but they will be non-perturbatively suppressed. This is the leading saddle. So the other things are down by some factor of e to the minus x. Okay. Is that clear?
You're asking about the definition of the boundary problem that gives you this solution?
yeah, maybe that's what I mean. What did you fix in the boundary problem?
Yeah. This is supposed to be usual ADS boundary conditions, where we take the length of the time circle to be beta. So, I mean, the easiest way to define the standard ADS type boundary conditions is that we first start with some cutoff, and then we take the cutoff to infinity. So we say that the metric along the boundary is fixed to something which is proportional to RC squared, where RC is a cutoff that we're going to take to infinity. This makes it have the correct units. And other fields are also fixed. Maybe there's some scalar field, it'll also be fixed, etc. And okay. And then we take, so this is the Dirichlet problem. And then we take RC to infinity. And if there are other pieces here which have, certain scaling dimension, we scale them with the appropriate power. Okay? So that's the standard ADS boundary condition. That's what I take here. So when I say that I fix beta, I really mean beta here where I factored out this RC. So it's like the CFT definition of beta in the context of ADS CFT. Is that clear?
Yeah.
Okay. Right. Now, so but this is kind of a mysterious computation in some ways, because one, you get, first of all, the fact that you get an answer is kind of surprising, right? It tells you that the entropy supposed to be microscopic entropy, can be computed from this smooth saddle, which looks like it's in the domain of validity of the low energy effective theory. And somehow it knows about the microscopic entropy. And it's kind of mysterious, what is it counting? Because this topology does not have a foliation by spatial slices, right? If I ask, let me slice this apart to get a counting of states, the way you usually would slice apart the Euclidean path integral to see directly what state is counting. Well, I start to draw the slice, and then, well, what do I do? So it doesn't go anywhere. So it's kind of mysterious. And the fact that you kind of get an answer is in a way an example of UV-IR mixing, the type that Nadi talked about yesterday. Here it's a little bit different. It says that there's kind of a constraint on the UV, right? So somehow the IR theory knows the answer, and so only very special theories that have some very special property at short distances will make this compatible with that. Okay? And that's going to be kind of the theme of the talk today. I think in Nadi's situation with fractons, the UV-IR mixing is sort of the converse, so that there's extra sensitivity of the IR, there's extra dependence in the IR, and here there are extra constraints on the UV. Good. Now,
So Daniel, just
Yeah.
to clarify, if you take the usual effective field theory and ask a question of this sort, you put some boundary condition and you ask how many different configurations will give you this specific state,
yes.
you're going to get less than what you get from the UV theory?
No, usually you simply, usually the structure of the computation is different. So I was actually just going to say this. So I'll say it. So a more standard situation is that the Euclidean saddle will look something like this. Oops. Something times a circle, where this is includes the configuration of the fields. Okay, so we'll have some setup like this. We have just a circle times a particular configuration. It's time independent, so we don't break time translation and invariance spontaneously. And the on-shell action, the classical term, is going to be beta times a number. And so that won't compute, oh, sorry, S there is the entropy, and S here is the action. Okay. That won't contribute to the entropy. This is just the shift of the ground state energy. And then, why do you get any non-zero thing from the entropy? It's because you compute the one-loop determinant. So when I compute the partition function, oh, sorry, I should have put here log Z.
It's log and a minus sign.
Log and a minus sign, yeah. We should also put here the one-loop determinant, so we get plus log of Z1 loop, plus higher loops, of course. And this is where a lot of the features come from, but when all of the UV modes contribute non-trivially to the one-loop determinant. And so that's the thing that gives you the sum over all of the UV things. But somehow in this geometry, it's different because the geometry just looks smooth everywhere. Okay, it doesn't have the structure of something times a circle. Okay? So this is the conventional thing. Now there are non-gravitational examples where there is a non-trivial contribution to the entropy from a classical term, and the classic example is in gauge theory, when if I could compute the thermal partition function of gauge theory in a manifold like this, I can have a Wilson line, which is the integral around the time circle of the gauge field. Okay. And sometimes there are phases where this thing has a non-zero VAD. And that corresponds to configuration which classically gives the contribution to the entropy. And maybe that's a hint for what's happening in this gravitational situation. And in this case, this Wilson line turning on has to do with the imposition of the constraints. Right? So integrating over this thing is what imposes the Gauss law. And so maybe that's a hint. But it's hard to know exactly how to interpret that hint. Okay? Good. So now, if one wanted to give a state counting interpretation to this Euclidean path integral. An idea is that you might try to cut out a little hole at the tip and put some boundary condition there, which is fictional. But maybe you would think, you know, when we discuss entropies, entanglement entropy in quantum field theories and the continuum, they have divergences. And the typical thing to do is to put a kind of brick wall, fictitious brick wall boundary condition as a regulator, do the computation, and remove it at the end. Maybe we should do that in this gravitational case, and somehow that will make everything make sense. So an idea is to cut out a tiny hole. This idea is not going to work, but it's useful to understand why it doesn't work. And I think this idea is really, in my mind, associated with the a priori possibility that, you know, the answer, of course, for the entropy of the black hole is the leading on to the famous A over 4G Newton, the Hawking entropy. And this procedure is kind of associated with the idea that maybe that comes from quantizing the diffeomorphisms across the horizon. Okay? That's, in a sense, what this sounds like, right? I would cut out a little hole, so now my Euclidean saddle, which computed the Bekenstein-Hawking entropy, so it got the A over 4G Newton. Well, now I think of it like this. The Lorentzian continuation of this thing is going to be the dotted line will continue some kind of stretched horizon. That's my brick wall. And, you know, maybe when I put some appropriate boundary condition here, it will end up, you know, counting kind of the gauge. You know, if I do some similar things in gauge theories, there's contributions to the entropy that come from the gauge constraint being cut at the boundaries. It's like I have to introduce extra modes to impose the Gauss laws. Maybe that somehow works for gravity, and A over 4G Newton is counting that. So that's kind of what this idea is about. But the answer, so let's see, it feels at the horizon. But the answer here is really no. So it doesn't work, and it doesn't work for a very particular reason. There's kind of a topological obstruction to this idea. A very simple place to see it, and I'm going to discuss some 2D toy models throughout the lecture, just not because the things I say I think are specific to 2D, but sometimes it's just, that's a place where we can get formulas and see things very explicitly. So if we were in this 2D JT gravity, which I've mentioned in the previous lectures, just as an example, well, then we can ask whether this kind of procedure could work. And here it might seem especially tempting because it's very simple gravity theory. In fact, locally in field space, perturbatively, it's equivalent to SL2R BF theory. This is the 2D dimensional reduction of the fact that pure 3D gravity is related to SL2R times SL2R times Simon's theory. What is BF theory? BF theory is a thing where the action is just trace of BF, where F is a field strength and B is a scalar. They both live in the adjoint here of SL2R. Because the group is not compact, the coefficient here is not quantized, and it's related to the ADS radius. Yeah. Now, this correspondence, as I said, works perturbatively, and the dictionary is very simple. There are three components. There are three generators of SL2R, three Lie algebra elements, and there are therefore three components of the gauge field, and the dictionary relates the spin connection to, I don't know, let's call it a 3. 3 here means the third generator, J3 of SL2R. And then there are two Zweibein components, so this is omega mu, and these are E's 1 and 0 mu, which is the 2D connection, Zweibein or whatever. And these will be related to the other two components of SL2R. So this dictionary is very simple, but if we try to read in this dictionary what the disk, which is the 2D black hole, looks like, there's something rather peculiar. So the ADS boundary condition says that the spin connection is trivial along the boundary. So out of the ADS boundary, we have that the holonomy of A3 0 along the boundary, because there's no twist of the frame along the boundary. But if we cut out a little hole around the origin, we want the integral of the spin connection to be 2 pi and not 0. Because this integral is just the cone angle around the point. And a smooth point means that the cone angle is 2 pi, not 0. So we cannot have a single valued connection with this property. But if we really said that the group is SL2R, rather than the universal cover of SL2R, there's a compact U1 in SL2R, then we could say we glue this patch to that patch with transition functions. So this is an allowed configuration of SL2R, but not a universal cover of SL2R. But neither one makes it work, because, so if we have universal cover, then we will have to have cone angle 0 at the origin, so it just disallows that. And if we say we have SL2R, well, we can allow this, but we also allow 0 and 2 pi n for any n. And we have to sum over them, and the leading thing is 0, which gives the divergent answer. Okay, so one somehow needs to impose this condition at this boundary that you cut out, and this condition is not a good condition for defining Hilbert space because it's non-local in time. If we had put 0 here, we could have had a local condition. A3 is 0. That's the usual thing in gauge theories. But when we translate gravity into this BF theory language, we need to impose this non-local condition. And that doesn't correspond to, you know, that's illegal. Oops. And in fact, we can say it a different way. In this 2D gravity can also be described in terms of the Schwarzian theory at the boundary, basically just the boundary gravitons, which look like reparameterizations of the boundary. So we have sort of some tau with f of tau. And in the Schwarzian theory, the Euclidean Schwarzian theory is defined by saying that this has to be a one-to-one map, a global diffeomorphism. And that one-to-oneness, in general, we could have a W-to-1 map, where the thing winds W times around the circle, and that W is exactly the same as this velocity. If we put here W, where W is an integer, that will also be good and loud, and that will correspond to the configuration of the Schwarzian where it's a W-to-1 map. And so, again, if you just want to quantize the Hilbert space, you will not get this kind of condition because it's non-local in time, non-local in Euclidean time. So it has to be sort of a rule added by hand to get the answer you want out of the Euclidean path integral, but it's not the answer you get by quantizing the Lorentzian theory. Or it's not the answer you get by taking the Hilbert space formulation and translating it into a path integral. And the fact that you, so you need to impose W equals 1. And in fact, imposing that is what gives you the area term. Okay, so you could say this is like insertion. We could have said that if W was 0, so the winding was 0 around the circle, that could be imposed by a local condition. And then we could say we insert a defect which has winding 1. And this defect gives the entire area term. This defect is the area operator. It's not too surprising because the thing naturally wants to have cone angle 0. And the cone angle is the, sort of rotation generator around the Euclidean horizon, which is conjugate to the area. So this thing just turns into the area term. So this constraint basically gives the A over 4G Newton term, and so we can't get it without putting this thing in by hand. So this idea doesn't work. Okay? So it's not just quantizing diffeomorphisms or some degrees of freedom of the low energy theory at the horizon. Maybe that's not very surprising, but somehow the possibility that it could be that continues to be investigated many, many times. So I think this is a very clear reason why that cannot work. Now, let me switch gears for a minute and tell you what the Hilbert space counting of states would look like. Okay, so here we kind of started with what we think is the correct answer, which we got from the Euclidean path integral. We were trying to force it to look like a Hilbert space counting, and that seems somewhat challenging. But what about if we go the other way? And maybe I'll say one more thing about this, which is, if we had some large number of degrees of freedom which lived on this cup, then we could try to just construct out of them a clock. Well, see, in order to impose this condition, that this is 2 pi, you need to be able to keep track whether you went around the circle once. Basically means that you need a clock variable. So if we have many degrees of freedom here, we may construct a very good clock, and we may be able to get this equation with w equals 1 imposed at least approximately. And somehow that must be a kind of cartoon of the mechanism, but it's hard to say more without a specific theory in mind. Okay, so how does the Hilbert space language count black hole microstates? And of course, sometimes we sort of think of the problem of black hole entropy as a problem of finding states that the theory didn't have, right? That the semi-classical theory says there's only one black hole, but it has this huge entropy, and there must be something else which gives that. And indeed, for the extremal black hole, that's a correct picture. So for extremal black holes, I really mean BPS. For the supersymmetric extremal black holes, there is only the empty static configuration as an allowed configuration with those charges. And the classical theory, the gravity theory on its own, sort of gives 0 entropy 1 state, if you like, or no states if we disallow the 2-sided configuration. And here we require more states than we had in just the kind of Einstein gravity plus Maxwell or whatever truncation. And those things could be D-branes or some fuzzball-like gravity solutions, etc. And these give some BPS configurations and can account for the entropy. Okay, so there, I think, in a sense, there's no conceptual mystery. Of course, there's a question of details. Why do you get the correct number? Right? Count D-brane configuration. Why does it end up equaling the area over 4G Newton? But there's no kind of tension or contradiction a priori. But if we're away from extremality, above extremality, then there are an enormous number of black hole microstates in the semi-classical theory. We really have an infinite number of semi-classical microstates. And it's easy to describe at least many of these states. An example are all of the states you get by collapse. See, when we're above extremality, there's nothing that tells us that the states we're supposed to be counting are time independent. Because there aren't very many static states. But when we discuss the black hole entropy, we're not supposed to be counting any static states. That's the Euclidean logic of Euclidean cells. That's not the logic of counting states. So there are enormous numbers of black holes formed from collapse. So those have, if we were in flat space, whatever, ADS, doesn't matter. There's a horizon, those are things like this. And we can, again, if we want to discuss Hilbert space, we should somehow fix temporal gauge. Maybe a nice way to at least perturb it in perturbation theory, we could try to fix temporal gauge, that is, the diffeomorphisms that move the slice up and down in time, with a condition like the trace of the extrinsic curvature of the spatial slice is 0, which is a maximum volume slice. This is a nice condition in low-dimensional gravity, 2 or 3 dimensions, and maybe a good condition in higher dimensions. Witten wrote some paper summarizing some aspects of this gauge choice several years ago. And so in slices like that, these maximum volume slices, the volume of the interior grows linearly in time, at least at late times. So it gets longer and longer and longer. And there are an enormous number of states associated to these slices. So black holes formed from collapse are not the most generic kind of state. In semi-classical theory, a more generic thing would be to take a slice like this, like the one that slices the black hole formed from collapse, but with more arbitrary data and treat it as an initial value slice. So that would give us a picture. Maybe I'll switch to ADS, I don't know why I do flat space there. Let's say here's the ADS boundary. Here's just the origin of polar coordinates. And we have one of these maximum volume slices. Maybe there's various fluctuations in it, gravitons, maybe there's some matter. And out here, there will be horizons, and here's singularity, and this is what the classical solution looks like. So here's some initial value slice, which obeys the Gauss law, on which the Gauss constraint has been imposed. And these are very special examples which, when you back evolve them, the black hole disappears, but a generic one, it looks like a black hole always. So this thing might be called a bag of gold, some configuration, in general, a very large region behind the horizon. And the number of these states is just unbounded. There's simply a continuum of them. So once you cross the threshold of forming a horizon, you get a continuum, and the continuum is associated with the fact that the length of the interior can be arbitrarily big. So if we're in ADS, this length is infinite because of the ADS boundary, but we take an ADS renormalized length, and this is unbounded, and that unboundedness is what gives the continuous spectrum of these things. Okay. In fact, this fact that there are these too many states is really the black hole information problem. Right? The point is, if I have a black hole like this, that's formed from collapse, and it starts to evaporate, eventually, at the page time, the coarse-grained entropy of the state exceeds the Bekenstein-Hawking horizon entropy. Because as this slice gets bigger and bigger, the coarse-grained entropy, the semi-classical counting entropy, grows linearly in time, and eventually it gets bigger than the area over 4G Newton. And then it seems that, the radiation that you sent out is, in the semi-classical analysis, everything looks unitary. The information you sent, the Hawking radiation that came out is entangled with this stuff inside, and there's a huge amount, huge entropy of stuff inside, so it's allowed to be unitary, but if we think that the Bekenstein-Hawking formula is correct, that's where something funny happens. So if you have a theory of gravity coupled, string theory, where when you count the number of states, you get the Bekenstein-Hawking answer, this theory cannot have an information problem. Okay, so that's another way to say it. So the entropy problem, so to speak, if you solve the entropy problem, you automatically solve the information problem. But here I want to think of it as kind of a constraint on the UV, right? We kind of took this effective theory point of view. We started with just Einstein gravity coupled to some stuff. Most bulk theories are bad. They don't work, right? You get infinity out of these questions, and something very special in the UV has to make it all work. Okay? And we want to try to focus on what is that. Now, well, this is kind of pictorial. Can one actually count these states more quantitatively? I mean, I said there's a continuum, but is there a formula? And maybe somewhat surprisingly, I think no one has ever really done this calculation very precisely, although it seems to be if somebody was like a canonical gravity person, you think this is how you would discuss the entropy of black holes, but nobody actually ever did this computation. It's hard to do it from the Lorentzian picture because you'll need to quantize the phase space of these solutions. That sounds like a hard problem. You could put some cutoff if we're in, higher than 3D gravity. But it sounds like a huge mess. But instead we could try to compute it from a path integral. But now we will use the orthodox rules of constructing path integrals from a Hilbert space. We will not use the Euclidean black hole. We'll just take this thing and Wick rotate this picture and ask what will that computation be. So that would be a computation which looks like this. Here's the ADS boundary whose renormalized length is beta, this at the temperature, and then we have some geometry here, which ends on some circle, and in this picture, what happens here, this was supposed to be the smooth origin of polar coordinates. So we have this picture times an angular sphere, and the angular sphere shrinks smoothly here, so that's what we put here. So we say that we also have this times SD minus 1, and this sphere shrinks smoothly. So this is smooth planes. This has the topology of empty ADS times a circle, okay? And one could try to compute this path integral. That's never been done. Sounds funny. Of course, what has been done is to neglect gravity in this picture and compute just the thermal gas in a fixed ADS background. That has a much smaller entropy. But that's very deceptive, right? It's crucial to include the gravitational back reaction to see that you have this continuous spectrum of states, this huge number of states, because you need this long warped throat region to support having what looks like it will be a huge mass, having very small energy measured from the boundary. Right? That's sort of the key point of these states. There's a huge amount of stuff in it, but it's very deep in the throat, so it doesn't contribute a lot to the ADM mass. So that's, you need to include gravity in this computation in an essential way. So I think it would be really interesting if that was done. But there's a related computation which has been done, where we consider a different kind of semi-classical black hole microstate, where instead of having, instead of the spatial slice just looking like smooth empty space, we have one of the extremal branes or fuzzballs at the origin. So the crucial point here is that we don't want the Euclidean time circle to shrink, because we're supposed to just be counting some states. But no, we don't have to take this angular sphere to shrink. Let's say there was some extra dimension. We're in a Kaluza-Klein compactification. There's some other manifold. It could be that this manifold has a piece which shrinks there. That will be a kind of Kaluza-Klein end of the world brane or fuzzball. Or we might just say there's a D brane here that ends the space or something like that. Now the kind of a nice toy model to discuss this case where there's kind of an extremal thing that ends the radial direction. And the only reason to do that is that computation is harder. That computation is harder, this one is easier. So an easier kind of microstate is where we have, so I'll just draw, I'm going to just focus on the 2 dimensions of the radial direction and the time direction. But there may be other dimensions involved, but I'm just not going to draw them. And I can just take the KK reduction of everything and treat it as a bunch of fields at the level of this analysis. So I have my ADS boundary, and then I have some end of the world brane. Here's T, here's the radial direction. And this is again, well, I draw a bad aspect ratio, so let me draw it again. This is again supposed to be a bag of gold. It has an initial value slice like this. The end of the world extremal object is behind the horizon. And then there's this singularity here. That will be the Lorentzian kind of configuration. So this is exactly the same picture as before, except that now I say this is not the smooth origin polar coordinates, but just a place where the radial direction ends. Right? And so I think in this situation, at least, a lot of the features can already be captured in the 2D toy model. So I'll discuss that just with specificity. But it's not essential. So we could take JT gravity, and then we just say this is an abstract end of the world. So we take this thing to be an end of the world brane, and it's parameterized by its mass or its tension. It's a 1D 0 + 1 object, so the tension is the mass, some tension mu. Okay? And if mu is positive, they always have to be behind the horizon. If mu is negative, there could also be naked brane solutions, as well as solutions where it's behind the horizon. And this problem can be easily solved in the Lorentz signature. In the pure JT theory. There's no propagating modes. The only non-trivial variable is this length of the slice. To fully fix the gauge, we require that the slice is perpendicular to the end of the world. And then it's geodesic, which is the 1+1 version of maximum volume. And we discussed the length, which is again an ADS renormalized length. And in terms of that variable, this thing is associated, can be easily quantized, and you get a Morse potential of quantum mechanics. It's very similar to if we had two-sided black hole in JT gravity, no end of the world ring. It's the same thing with this in a factor of 2. Okay. And if mu is positive, this is just a reflective potential with no local minima, and you have only scattering states and the spectrum is continuous. And again, you see that the continuous spectrum is associated with the fact that L is unbounded. Okay? It's the extremely long interiors which make the spacing vanish. If mu were negative, then there could be a well. The well is associated to the naked end of the world, and you'll have some discrete states. And then a continuum above the black hole threshold. Okay. And one can, count the divergence of the entropy associated to this continuous spectrum by doing Euclidean computation, which now looks like a trumpet. Because we're in JT gravity, the equation of motion is that the curvature is -2. It's very simple because it's pulled by constraint by the dilaton. Here's the end of the world brane, and let's say this has length b, and this has length beta. This configuration is not a saddle, it's just the most general off-shell configuration. Once we impose this, which is really imposed as a hard condition because the dilaton is the Lagrange multiplier. So this path integral can simply be done. Looks like an integral over b. There's a factor like this, e to the minus b mu, which comes from the energy of the end of the world brane. And then there's a factor from the Schwartzian fluctuation of the boundary, which is some number, the dilaton value at the boundary, maybe there's a constant on the forgetting, b squared over 2 beta. And then there's a measure factor, which you can either derive from this quantum mechanics or by carefully gauge fixing this trumpet problem, and the measure factor looks like this.
Does this system have a plane wave normalizable ground state? I mean, is the
Yeah.
spectrum from 0 to infinity open or closed?
That question might be too subtle for me to know the answer to, Eliezer. I'm not sure.
It's probably not.
It's probably known because I think the Morse potential quantum mechanics is very well studied. I'm tempted to say yes, but I'm tempted to say yes.
Are you fixing that this brain is a geodesic?
No, it's not a geodesic. Oh, sorry.
Or what boundary condition?
Oh, yeah. On shell it does hold a geodesic. Yeah. It's a geodesic. So right, I mean this is sort of the simplest kind of end of the world brane, where you don't. So the kind of conjugate pairs in JT gravity, right, are like the metric and there's the metric and the normal derivative of the dilaton. Write it like this. And then the dilaton and the extrinsic curvature. And so at the ADS2 boundary is like fixing these two, and these fluctuate, and here we fix this to be 0, and this, the opposite. So it's a geodesic. We don't fix the dilaton value at the brane, and we don't fix symmetric along the brane, but it's false geodesics, and this thing gets fixed because this is set by the mass, because this is like the Gauss. This is basically the gravitational field, and so that's set to be mu.
And the point of this is that you can take into account the gravitational path integral and see if you get an entropy smaller than e to the s naught.
Right, right. Well, right. So I mean, well, anyway. So this thing gives a number of states, which is easy to compute. It's computed by this Euclidean formula, and the answer is infinity. Okay. So the answer is infinity because it's small b. It looks like integral db over b, and so it has a logarithmic divergence. And the fact that it's a logarithm is associated to the fact that the reason why there's an infinite number of states is just because the length is unbounded. And so if we looked at, if we looked at the entropy in states where L is sort of less than some L max, like a cutoff, if we just by hand, then we would find that the answer is like log of L max. It's just like a box with size L max. And this log is the same as that log. So to beat the Bekenstein-Hawking entropy here, which you need to take the length to be exponentially large. So you get too many states once we allow the size of the interior to be exponentially large. Now we can also and should consider the theory with matter, which is a much better model of higher D gravity. And when we add matter, then we should insert into this path integral the bulk partition function on this geometry. Like if it's free fields, it's the one-loop partition function. This is the kind of thing I talked about in the previous lecture when we tried to write a matrix model for JT with matter here in this trumpet configuration. But at small b, it looks like we get a thermal divergence associated to this very small circle and a long neck. And so at small b, this thing is approximately e to the c over b, just the thermal entropy. And so now this function has a huge, terrible exponential divergence as b goes to 0. Many, many more states than in pure JT, not surprisingly. And in this case, the entropy, if we restricted the length to be less than some maximum length, doesn't go like the log of the length, it's just extensive in the length, because we're just putting a gas of particles, whatever is in this matter theory, in a box of some size. So this is proportional to L max. And so we will start beating the Bekenstein-Hawking entropy once the size of the interior is of order the Bekenstein-Hawking entropy, which is like the page time in these 2D models. So it all fits together. Now, so it's clear that something has to remove many states. Here, really infinitely many states. Something has to get rid of them. And we should think of the thing that gets rid of them as a constraint on the theory. Right? It's a constraint on the theory. If pure JT gravity is a well-defined theory, it gives this answer. It doesn't get rid of the states. It just says there are infinitely many states. Or pure JT gravity coupled to a CFT, which is finite in the UV. It's also defined, but it doesn't give a good answer. So we want to say that those theories are in the swampland. So it's really that these states should go away is a constraint on the theory. And we can try to ask what does that imply about the UV? Now, I guess there's no reason to move it because all of it's filled with stuff. So well, again, we can try a wrong attempt. It's also, I think it's a very illustrated wrong attempt, which is induced gravity. And I don't mean to say that some form of induced gravity might kind of be the answer, but it cannot be induced gravity from local quantum fields, and we're going to see why, at a very rough level. So we might try that. So what do I mean by induced gravity? In this JT context, the problem, right? We can let's say the problem again in a little bit more of the similar words to how I first presented it. The computation that seems to follow from the rules of Hilbert space, translated into path integrals, says that we have some cusp-like geometries that dominate. The B goes to the zero limit of the trumpet, which is the cusp. The cusp has cone angle 0. Theta is the cone angle. On the other hand, we want, so this is a Hilbert space, and this is the Euclidean, the usual Euclidean path integral. We have angle of 2 pi, a smooth point. So if we had a theory which had very short, yeah.
Where's the horizon in the Hilbert space picture?
Well, there's no horizon because this is a Hilbert space translated into a Euclidean path integral. And so we should never ask about where horizon is in the Euclidean geometry. We should ask where horizon is in the associated Lorentzian configurations for which the Euclidean thing is counting, but it's always counts them through some rearrangement. The Lorentzian geometries that are counted by that path integral are this picture. So they're time dependent. The configurations that it's counting are time dependent states, which have a horizon
Yeah, but here,
and a long region behind the horizon.
here you have a clear horizon in this picture, right?
Right, there's a horizon.
So I'm asking where is this horizon in the trumpet? Or?
It's not in the trumpet because again, when we're trying to count the entropy, we count entropy of time-dependent configurations, and then if we try to do it by using the Euclidean method, we have to do the whole path integral, but we usually look for a Euclidean saddle, which will be a time-independent configuration. So it's not that it's not the case that the Euclidean saddle, analytically continued to a Lorentz signature, looks like every single one of the Lorentzian states I'm trying to count. That doesn't make sense, right? So that's the situation here. If I try to, so first of all, this trumpet was an off-shell configuration, but it has a saddle at infinity, which is the cusp limit. When B goes to 0, it becomes kind of singular saddle. It's an infinite cusp. And the infinite cusp geometry is time independent. If I analytically continue into a Lorentz signature, it looks like the L goes to infinity limit of those geometries. So kind of an infinitely long, well, I mean, that's not quite the right way of saying it, but it's, so it's like the extremal black hole. It corresponds to the zero energy state, where, its Lorentz continuation would be kind of like this. It's just the wedge. And this length will be L renormalized, equal to infinity like in the extremal black hole. So it will be the extremal configuration. But that's not it's not only counting that, right? Sort of the fluctuation determinant around this counts the rest. And you can't see in this picture where the horizon is of the fluctuation geometries. But that's typical. Yeah. Okay, yeah, good question. Thanks. So, induced gravity. How will this work? So, if it were the case that at very short distance in the bulk theory, there were no terms, so let's say in the UV, if we had no term that looked like the dilaton times the curvature and no term that looked like the Gauss-Bonnet, then we won't be able to distinguish this from that, because in the local region here, near the cusp point, the thing that tells you the cone angle, right, the cone angle is given by the Gauss-Bonnet theorem to the integral of the Euler density in the interior. So if we don't have these terms that involve the curvatures, then these two geometries are the same, and they might be equal, and it might work. And so we might imagine that in the UV we don't have this term, but we have some other scalar field. Maybe I'll call it, I don't know, chi, to distinguish it from phi, which is maybe just minimally coupled and coupled to the dilaton. So you might have terms in the action that are like, G mu chi, G mu chi, or something, and maybe it's massive. And maybe there's some term that also involves the dilaton in order to generate this. If we integrate out this chi, if we have this term, when you integrate it out, it will generate a cosmological constant and this kind of term. And if we put a coupling to phi here, it will generate this kind of term. So things like this could generate these terms. So you might think, well, maybe that's the answer. But it turns out it always generates them with the wrong sign. Okay? And there's a good reason for it, because if we think about the Lorentzian states, this is some modification of the theory in the deep UV. So how can that get rid of all of these states? These were not very UV states, right? I mean, this was some nice IR configuration. It was low curvatures everywhere. The dilettante didn't have any extreme values. Well, why would the short distance modification eliminate states? And well, the way it works is it has this chi has to be ghost. And what happens is that it doesn't eliminate the states. It just gives a bunch of negative norm states so that when you include them all together, it can cancel. So this is not a physically good mechanism, but I think it's illustrative of sort of why it's not trivial to solve this problem. Okay. Now, I still have like 30 minutes now. Is that correct? Yeah. 25. Okay.
Could it be that it follows some gauge fixing with the local symbol is
Sorry.
not manifest or something? Why should you get such a good?
No, you shouldn't. I mean, this is a failed attempt. So.
But Daniel.
Okay. Just like the other idea was a failed idea. Okay, so, now it's starting to do that buzzing again. I don't know what causes
First
that.
disentangled, then
Yeah.
lower.
Okay, but now it's not even working, right? It's too far. It's working? Oh, okay, great, okay, beautiful. Right, so I mean, one possibility here is some redundancy, right? Somehow the too many states of the bulk theory are not all different states, and that's been suggested by a variety of work over the past several years of other people, and maybe Netta will discuss it in her later lecture, I'm sure. And what do we mean by redundancy? Well, when we discuss these bulk states, we have to fix the gauge, right? We have to fix temporal gauge. If we had not fixed the gauge, then of course we will overcount the states enormously, right? We will overcount the states enormously. So for example, if we thought about the bulk, Hartle-Hawking state, if we were using the Wheeler-DeWitt formalism in the bulk, then we would write, some wave function of metric on a spatial slice with no constraint, nothing like the constraint that the trace of extrinsic curvature is 0. That's what Hartle and Hawking and Wheeler-DeWitt discussed. And then, we can think of it in a gauge invariant language as the overlap between a phys state in the physical Hilbert space and some kept state, except that these kept states are not linearly independent. They have large overlaps, which corresponds to the fact that this thing must obey an equation, which is the constraint equation. So those are two equivalent ways of discussing local constraints. So that in the Wheeler-DeWitt case, this thing is not even close to delta. Many of them are the same. We can even see it in the classical limit, just the statement that you can slice the same Lorentzian manifold by many different spatial slices whose induced spatial metric is totally different. And so they're not independent at all. They're highly redundant. And that redundancy tells you that this is not an independent data, but it obeys an equation for which the local part is the Wheeler-DeWitt equation, the Hamiltonian constraint equation. We could do the same thing in
JT gravity now? Or?
In higher D, or in JT. In JT, I would include the dilettante.
Of the other matter fields in the wave function.
Yeah, everything. And if I was in JT gravity, I would also need the dilettante if I'm discussing it in this way.
I
Hmm.
opposite, it's the bad thing, because if I have something like Polakov theory and think about that as theory of 2D gravity, then I have a
Right.
graph there, which is a time direction.
That's right.
Right,
Um,
and it's, then the theory is,
Yeah, I mean, well, in a sense, that is the reason why string theory, the world sheet of string theory does not have this kind of divergences, right? It's because the central charge is 0, including the ghost. But, okay, I don't know what to say.
For
But
the reason.
well, it's eliminated at the end by a constraint, so, because gravity eliminates some, 2D gravity eliminates some degrees of freedom, so even
Right.
it's not.
Well, yeah, it could be, but you know, if we think about T gravity with matter, then these will look like some peculiar kind of ghosts that we just added by hand. But okay, so it's an attempt that has not been made successful in this context. Okay, let me come back to this. So but we didn't use this kind of covariant formalism. I was kind of presented everything in a particular gauge, looked where we fixed the Hamiltonian constraint equation, at least in perturbation theory. This maximum volume slice gauge, and in 2D it's especially simple, right? It just says spatial slice is a geodesic. Trace of the extrinsic curvature, I mean the extrinsic curvature is 0 when there's only 1 + 1 dimensions. And there it's really a very good gauge in perturbation theory in low dimensions. But although it's a good gauge perturbatively, maybe there's a Gribov problem, so that you know these L's are somehow also not equal to delta. Well, so perturbatively they are, but maybe there's some tiny correction. That would be the case if it was something like a Gribov problem, but a Gribov problem, you usually imagine it's more classical, right? It's just, you know, somehow there are two different geodesic slices in the same classical space-time. It's certainly more subtle than that. But maybe there are other kind of non-perturbative corrections to the inner product, which come from the short distance physics. Maybe there are some other objects in the UV. And so it is logically possible for that to fix the overcounting in the sense that if I look at the matrix of inner products, it started as the identity. Let's regularize L max to write a finite matrix, but we can take the limit. So we start with the identity matrix as the matrix of the inner product is some k by k matrix, where k is much, much bigger than the Bekenstein-Hawking entropy because we have this overcounting. And then we add to this matrix another matrix where the matrix elements have sort of complicated and have typical size e to the minus s. So let me write it bigger. Matrix elements have typical size e to the minus s over 2. Then in such a matrix, it's possible that the rank could be e to the s Bekenstein-Hawking. So that's mathematically possible. Of course, it looks like a fine-tuning of order k squared, where k is much bigger than e to the s Bekenstein-Hawking. So that is a pretty dramatic fine-tuning if we don't have any principle to understand why this matrix looks the way it looks. At some level, this is the answer, but it seems that there must be some miraculous property of the bulk theory, of correct theories of gravity that will lead to this kind of answer. And we'll see if we can say a little bit about what that might be. But let me elaborate on this a little more. This is the picture which is kind of suggested or implied, or an average version of this picture is what is implied by these computations with Euclidean wormholes. So by computations with Euclidean wormholes, I mean things like the connected contributions to the square of the spectral form factor, or so. So I might have these kind of double trumpet contributions which reproduced the ramp-like feature in the square of the spectral form factor, or if I, in the computation of correlation functions, well, kind of continue to Lorentz signature, but let's draw this picture for simplicity. If we look at correlation functions in the black hole at very late times, they don't decay all the way to 0. And you can see that by including some Euclidean handle where the particle goes through the handle, and so it doesn't have the decay because this distance is much shorter. So this is kind of the e to the minus s residual in the thermal 2-point functions at late times. So these are other kinds of Euclidean gravity computations which don't immediately have clear Lorentzian interpretations. But what they really correspond to is this sort of an average over this mechanism. And let me sort of explain a little bit why that's the case in this language. So let's suppose we look at this overlap. So we'll go back to pure JT gravity, and we look at this overlap. In pure JT gravity, we have to go to ultralate times to see the overcounting. Remember, you have to go to times of e to the s to see an overcounting. If we had matter, it happens much faster. Time scale of order s. Huge difference, but it's just easier to discuss pure JT. And I think for this question, the point is similar. Now, what is the overlap? Well, we can draw a path integral to compute the overlap. Here's the ADS boundary. But we didn't put any time evolution, so we will put the two things at the same place in the ADS boundary. It's just a pure, so there's no propagator piece. It's just the overlap. Here's the end of the world brane. And we will have a slice here of length L and a slice here of length L prime. And if we put nothing in between it, we just get the delta function that just says that it's a basis. Okay? But if we compute the square, we have two of these pictures. And with two of them, we can now try to connect them with one of these replica wormholes, which goes like this. And this gives a non-zero answer. Okay? This gives a non-zero answer, which is down by, factor of e to the s naught, the genus counting parameter. Some e to the minus s naught correction. But it's not factorized, so it sounds sort of strange. It's a contribution to the square, but not to the object, and so on. But it says that there are these exponentially small corrections to the inner product. And because you take the square, somehow it's an averaged version of this effect, so you need to take the square to see them, otherwise they cancel out, because it could be positive or negative. Well, that says that you have them, but are they the right ones? And well, one can do the following little computation, which is meant to be computation not in this sort of disorder averaged story, but in some specific theory that we don't know, where it works by a miracle. Okay, so let's imagine we have a theory that looks like JT at low energies, and then there's some other stuff at high energies, plus some unknown or to be determined UV. Okay, and I'll parameterize the UV in a simple way. So in this theory, how will we do the thermal computation? Well, now we're going to use all sort of the Euclidean rules and see that they give a consistent answer to the Hilbert space rules if this is determined in the right way, which corresponds to that kind of mechanism.
Is JT supposed to be the IR flow?
Yeah.
It's not that there is in the UV also something else which flows to JT. It's
Yeah,
in the UV you want to.
Right. I mean, it's JT at low energies, and the UV is to be. So there's something to be determined in the UV, and it flows to JT at low energies. That'll fix it. And so if we were to compute the thermal partition function, z of beta will have the disk term. That's the usual leading JT answer. And then we'll parameterize the UV by a piece like this, some kind of trumpet, and then there's some stuff. And we will say what we want x to be in a moment. Okay? But x of b is supposed to parameterize the fact that the UV is something else. Okay? So if we want to have our cake and eat it too, so to speak, we can imagine that somehow x of b is the, so this is a specific answer. This is a known function of b and beta. It looks like this e to the phi b, b squared over beta, and maybe there's a measure of beta, integral db, x of b, that's this contribution. And if we get to pick the function x of b, then we can get any answer we want, and in particular we could get this answer, which is, I think, the answer we would like, where the EI are a discrete collection, and of course we could get this answer for any collection EI if we pick xb to be what we want, right? Of course, because this has this particular spectral density, the smooth spectral density you'd extract from this looks like a cinch. If the EIs are a delta comb which is well approximated by the cinch, then this x doesn't have to be as dramatic. But so that's kind of the natural situation. But we can think of this as the spectrum of the random Hamiltonian of the SSS model, for example. And so a given instantiation somehow corresponds to a theory where this is the answer, but we don't know why, right? What is the gravity description that led to this or this? Okay, we're not saying. So this is not meant to be an answer, but just kind of just to draw this thread together with this story of Euclidean wormholes. Then we can also compute the inner product with the end of the world brane, these states. So we look at this overlap L and L prime. So there's this piece, which is delta, L minus L prime. And then there's, L prime. This is length B. And again, we put the blob with all the stuff. And we take the same x of b. Okay, so at least we use a consistent set of rules. We put the same x of b, we'll get some quantity here. I won't write the formula like this at the time. But this part of it is something solvable. It just depends on the Morse potential wave functions. Yeah.
Is it the Lorentzian Euclidean?
Well, this is also Euclidean, if you like. I didn't tell you what this might be. This might need to be Euclidean signature if it's some handles or something. So if we add this with the same x of b, maybe it's not very surprising, but the answer turns out to be this. In other words, it inserts the projector onto the same collection that you would get here, so there's kind of a compatibility. So if we're in this miraculous theory, then there's a compatibility. Okay. Maybe this isn't very surprising because, okay, we didn't say what theory gave us this x, right? So again, we're left with the question of, what? So maybe there's these redundancies, but still we kind of need to find a mechanism. And I think the answer is supposed to come from theories with extended objects which have a Hagedorn spectrum, because if we kind of saw this a little bit in the second lecture in the double trumpet kind of configuration in the context of the matrix model. Here we had, let's go back to what looked like the natural computation, the thing that really counts the states from the Hilbert space point of view. That was this kind of trumpet, where we have the end of the world brane here. And then we said we put the matter partition function. But let's say the matter theory has a Hagedorn spectrum. Well, if the matter theory is string theory and has a Hagedorn spectrum, then this path integral will, take the form integral over b. Well, at at some, near BH, where BH is the inverse of the Hagedorn temperature, the integral will be dominated by this pole, and it will give a simple pole at the Hagedorn temperature instead of the exponential divergence at b equals 0. And this is associated to the fact that there are extended objects that wrap this circle, which become massless when the circle is very small. And so what you really want is to condense the circle, to condense those objects, and that will close the circle. Okay? So somehow that's supposed to be the mechanism that ends up converting this kind of computation into the thing that looked like the Euclidean black hole saddle. But this is kind of an example of there being redundancy between the states, right? It's just sort of a mechanism that explains why. So in other words, from the Lorentzian point of view, if we ask what is this trumpet thing computing, even in string theory, it's doing a computation that it counts states which look like a black hole, where deep with an enormously long throat behind the horizon, which ends at some extremal end of the world brane, some object of string theory, with many even low energy excitations in the throat. Those states are still there. What this is saying is that they're all redundant because there are some extra gauge symmetries that we didn't impose correctly. So somehow it's still somehow some story of redundancy, but it at least at the level of this Euclidean path integral, is a clear mechanism. And we know that there are dualities which relate this trumpet type of picture to the black hole picture. For example, the famous FCZ duality of two-dimensional string theory is in a way an example of this mechanism. So in the FCZ duality, it's a duality between, on the one hand, the cigar CFT, that is string theory whose target space is a cigar. Cigar is a 2D asymptotically flat black hole, but it's a asymptotically linear dilaton. So it's a string background where the dilaton looks linear at infinity. So actually, if we go to Einstein frame, the metric looks ADS at infinity. And so this is one side of the duality. This is the black hole side. And then the other side of this Euclidean duality is a free linear dilaton theory on the cylinder. So we have, so again, here's this radial direction. Here's the boundary region when R goes to infinity. This is R goes to infinity over here. Here, the radial direction stops at this place, but here it goes all the way. But the dilaton is linear in the whole geometry, so this region is strongly coupled. So we get strong coupling here, and a winding condensate is turned on. So on top of this free theory, so we have this free theory deformed by an action that looks, so this is the world sheet theory. So this is an integral over the world sheet of some winding operators, one winding and one anti-winding, so we have the sum of them, which is real. This thing is dual to this is an exact world sheet CFT duality. And again, if we took this picture, this string theory in Einstein frame, it's exactly this hyperbolic cost, because we rescale the metric by this the exponential of the linear dilaton, which is an exponential factor, and it makes it look like this hyperbolic thing. So this is really an example of that, I would say. And an important question here is what is the Lorentzian meaning of this picture, right? And so I could give another whole lecture on that, but I won't. But let me say a few words about it, and then we will wrap up. So, no, I know I have no time. I think I have five minutes, yes? Good. So what would be the Lorentzian meaning of this? Well, we kind of have to go back to how the world sheet works. So let's pretend so this theory, has a peculiar feature, which is related to the fact that there's a strong coupling region. Normally, if I take a world sheet CFT, which is here starting, say, with a free theory, and I add a deformation, it will be something that I will do computations in conformal perturbation theory. And the coupling here, which I might call lambda, would be an exactly marginal parameter of a family of 2D CFTs. That's not the case here. In fact, there's a symmetry of the original free theory, which involves shift of the radial of the R variable, which is a field of the 2D CFT, that rescales these and can shift lambda. So, and this is not a small perturbation. So that's another way to say why perturbation theory in lambda doesn't work, because this operator grows very large. So these operators have a piece which is exponential in the radial direction with some parameter b. And so it's a very large deformation here. Okay, so it cannot be, the amplitudes are not in power polynomial functions of lambda. So that makes the story a little bit more subtle, and it's related to this strong coupling. Let's suppose we can ignore that for a moment, and we just think about an amplitude where there are a specific finite number of insertions of W plus and W minus in the free theory. Perhaps by analytically, sometimes that does control the answer for special choices of quantum numbers, and then we could try to analytically extrapolate away. Or we could try to regulate the strong coupling region in some way. That will take us away from doing an exact CFT. We will put some wall there in some artificial way, and then we will have a power expansion, and we'll have to resum everything to get the answer. But let's just try to get an understanding of the meaning of this deformation. So the kind of computations we might do in this theory are things where I have a W plus and a W minus. Let's consider the simplest amplitude. That has the minimum number. I could always have more. In general, I have many of them. And then I have other kinds of vertex operators, depending on what I want to compute. So this is the tree-level string diagram. What does this mean in the Lorentzian theory? Okay. So normally we don't have a problem with that. The subtlety here is that this is an operator which is about winding around the Euclidean time direction. So what the heck does that mean in the Lorentz signature, right? Now, what we should, an important point is that we usually, of course, associate vertex operators to scattering states. Another way of saying it is, I think a very nice way of thinking about it is if you just do the CFT computations, there will be divergences in the integral over moduli when two vertex operators come on top of each other, which need to be regulated by some analog of the I epsilon description. And that translates into saying that in the vicinity of one of these operators, I can think of the world sheet as long tube near any insertion. And in this vicinity, the I epsilon prescription is equivalent to taking it to be Lorentzian on the world sheet, with this being the time direction. And that is, in a sense, some abstract or kind of formal point of view, why the vertex operator defines a state of the Lorentzian theory. But with these operators, the structure of divergences when things come on top of them is different. They do not have a coincident point divergence. Rather, if this operator has real momentum in the Lorentzian sense, because this has winding, they're not mutually local, right? This will be mutually local only with things that have frequencies given by the real Matsubara frequencies that are periodic. And so when you take this operator near this one, when you go around, it seems to be not single value. And the way around it is, again, you need to change the contour of integration of the moduli. You can do it in such a way so that the final amplitude you get is the same as if you had done all Euclidean computations and then analytically continued the answer, right? But here we want to do it with the correct vertex operators with the correct prescription. What it corresponds to is take analytic continuation in that to be time. So instead of having this tube in the region around one of these, we get a kind of Rindler-like region on the world shape, and we integrate the operator that's near it along this region. Okay? That's the analog of this. If you believe that, then you would say this gives us the Lorentzian interpretation of these operators. It's some angularly quantized Hilbert space where it looks like we have a string which ends on this operator. And that makes a lot of sense, especially in this kind of situation where they're associated with a strong coupling region, and we can think of it as some string that comes in and out from the strong coupling region. So that's the suggestion, a suggestion here. But I think in general it would be very interesting to understand these kind of string dualities, which seem to give the mechanism that fixes this overcounting problem, and try to translate them all into the Lorentzian language. We will really see what eliminates very precisely all of this too many steps. So that's left to the audience for future work. Thanks.